All right, so this is the main screen of the HMI. Here you can see the robot operation as well as the camera operation right here next to it. So this right here will give you not only the status of the camera and the robot, but you can put the camera in setup mode and put the camera in run mode from here. Your run mode means that it can like actively do scans. It's essentially your auto mode for the camera, whereas like setup mode is the programming of the camera. Then up here at the top, we're taking account of the total scans that we're doing, how many okay scans there are, and how many not good scans there are. Obviously, this is not a normal production situation. We're scanning a bunch of bad hooks, so that way we can train the vision system to perform at its best. Down here, we have our data history. So data to the robot, data of the right hook, data of the left hook. I'll take you to the data of the robot. So this is the offset data of the robot, where the robot will essentially be doing its shifting if the hook is bent. So if the hook is bent, the robot will shift according to these data positions. So we're storing 16 registers or 16 positions of data, and you can see this data is coming in pretty tight. We're looking at this in millimeters. So this is 0.45 millimeters, 0.39 millimeters, 0.47 millimeters in the negative direction. And as you can see, we have -1 millimeters in Z, and it's pretty consistent all the way down, 0.20, 0.16, 0.14. And then we can go look at the, let's say, the right-hand hook data. So now we're looking at the right-hand hook individually. So this will help us detect if it's the left hook that's causing the problem or the right hook that's causing the problem. Because when you're looking at this data over here back in the robot screen, this data is the raw data that comes in from the camera, and then some math applied to it, some different equations to get us to this proper offset positions. These status screens are more of your operator user interface. So here's where you're going to get the status of an okay hook or a not okay hook. So we're looking at left hand independent, and then down here you also have right hand independent as well. So this will tell you if the XYZ data is close enough for the robot to offset and then place the part there. And it's also detecting special defect conditions such as a twisted hook or a bent hook. So there's separate tools that are in there to measure for these. These XYZ offset values will also fail, not in all conditions, but they will fail in some conditions where the XYZ value is just too large, and then the hook will fail. But these give you a actual indication of why they failed. And then we're also giving the data that you can look at to see by how much it failed. Now over here you have what is the master data. And so what the master data is, it's essentially the raw data coming from the camera. We then scan in a perfect hook. We then master that data as a perfect hook. And then that data gets stored here to then apply our math to. So right now the camera's actually giving us a 65 point, let's say 250 or something like that, right? And that's why we're getting a negative 0.235. I'm just giving you rough numbers, but essentially we've zeroed this data so it's much more easily readable, and you can observe it much more easily. So if this data was just coming in raw like this, you would see it bounce around at 65, 65.1, 65.2. And then you have to track that for all these data points. It's almost impossible to track that many data points without zeroing them. Whereas if you zero the data, I can come over here and I can look at this data and say, oh, okay, everything except for Z is coming in under 1 millimeter. And so if I see this data and then all of a sudden I see something come in at 5 millimeters, then you can very clearly indicate that there was an issue on that one. Especially if it's still okay, but you're just trying to overall just observe the data of the hook. This gives you that capability. Then down here in the bottom left corner, you have a left-hand hook tolerance. These are all your tolerances, right? X, Y, Z, as well as the twist and the bend. So this is the thresholds that essentially tells the system whether it's a good hook or a bad hook. Now, when it comes to the XYZ values, this will also prevent the robot from being able to do a offset. So if this value becomes too big and it fails, if this data fails, then the robot can no longer place to that position. And the reason for that is because the robot may crash in that particular condition. If it tries to offset too much, it could then put the robot into a crash condition, could crash the cameras, could crash into the rack. So that's why these thresholds are here. And it's just important to keep in mind, not only do they control a good and not good hook measurement, but it will also prevent the offset position of the robot as well. All right, so here is the offset data to the robot. So this is where we're taking in the combined data from the left-hand side and the right-hand side, and we are utilizing this for the robot's offset. So up here you'll see the master data, save push button. So in order to master the vision system and to master the entire system, you need to select what is a perfect set of hooks, and then you need to scan that perfect set of hooks. I would suggest scan them multiple times, and then after you perform that scan, the tools inside the camera look good, click Save Master Data, and then it will then update these values to set that as the new reference for what a good hook looks like. So that way that you can take the most perfect version of a hook and call it, the 0 position. Or if ever you go to change the style of a hook to some degree, maybe you change like the length of it and it messes up like the Z value to the robot, then you can just remaster, scan, remaster, and then the system will be back up and running again. Now, there's a caveat to that, is if it's off too much where it messes up any of the vision tools, then you'll have to go in and modify the vision tools. And if the modification is significant enough, then you will have to go back in and reteach a new reference image in the vision system. All right, so now we're over in the Keyence vision software, and basically want to run through the different tools that we have and kind of how we have them set up. So you can see we have everything, all your tools here organized from left hook and right hook. All the tools within them are basically the same tools, and we're utilizing the tools in the same manner, which makes sense because the hooks are the same. This is also a list of all the different tools and the tool IDs, which is this T number right here, tool IDs that are associated within this left hook group. So I can right click over here and then you'll see the right hook group. And also another thing that you'll see is that the display is changing according to like these different tools that are here within the software. So going back over to here, the tools are the same, just the tools that are being displayed right now are different. So this is a combination of, I want to say, all these different tools you see here on the side. So to click into that and to break down what the tools are and what they do, I'll probably just do them for like the left-hand side since the right-hand side is the same. But they both have what we're calling a master tool. So this master tool is doing the initial identification. So this tool needs to be working appropriately for any of the rest of the tools to be working, because this does an initial identification that then locates where the part's at, so that way we can perform all the other tests accurately. So going inside this master tool, this is the search region of the camera, and this is the area we're looking to be a match. Now the data that we're utilizing for this particular tool is the angle data. So we're using this for the bent hook test. And then that's the only data that we're actually utilizing from this tool to do a pass-fail. We're then using the robot X and Z data to pass the offset values to the robot. And so we're using this X and Y. So X is X of the robot, and then Y is the Z of the robot. So we're utilizing this tool to then identify these individual lines here, where you can see we're identifying these lines, and then we're saying to the intersection of those lines is where we're creating our, let's say, offset point for the robot to move to. So that's basically our X and Z to the robot. Then I have the robot Y here. So the robot Y is essentially detecting how far away the robot is to and from the hook. And so all these different tools need to be utilized because the tool just doesn't offer the data points that are needed to perform each operation. Now I'll go over here to this twisted one. So pretty self-explanatory. These have all been named fairly identically with what the actual process is. So this will detect if the hook is twisted. And then we're also testing if the hook is bent front to back in another tool. Before I move to that one, I want to just say we're utilizing this angle from horizontal as our data point for how much angle is in this part. So right now we're getting at 2.5 degrees. Now this 2.5 degrees has been zeroed out in the PLC to then, this is a good part. So this is actually giving us a 0 degree angle through our master data, because this is what a good hook looks like. Now I'll take you over to the bent front to back. So again, the reason why we have the one tool that's doing bent left to right in that master tool is because it can detect the rotation in this 2D flat plane. However, this is a front to back type of motion, so we have to detect degree angle in a different way. As you can see, this degree angle is just automatically coming in from the camera as pretty much a 0. Just not all things work out like that. Like if we go look at the XYZ intersection, you'll see that this is X65, Y16. And then if I go over to the right hand hook, the right hook, and I go to that exact same tool, you'll see the values are completely different. And this is another reason why the data has to be zeroed. So this data is coming in as a 153 in X, and also coming in as a 19 in Y. And that's because Y is the Z direction. So up and down, they're fairly similar to the same height, but left to right, they're in two completely different places within the vision's, let's say, field of view or coordinate system. So that's pretty much the rundown of all the different tools that we're utilizing within the system. Obviously, we didn't go deep into like what each tool is doing specifically and how it operates, but that gives you an idea of each individual tool that we are using and a little bit of how it's working and where we're getting our data from. Now let's take us back over to the HMI where we're looking at the robot's data. So we'll go over here, data to robot, and just look on this screen. I like to look on this screen as an engineer because this shows the data over time versus the other one's just like, this is the data for this last scan. So what I'm gonna do is I'm gonna go over into the teach pendant, and I'm basically just gonna command the robot to scan at a different hook set. So right now, this entire time, we've been scanning on hook set number 3, which we're identifying as hook set number 1 is closest to the robot, hook set number 2 is the middle, and hook set number 3 is the furthest away from the robot. So we just scanned in hook set number 3. We're now going to scan hook set number 1. So we're doing this to manually command the robot through some values. And as you can see, we did that semi-autonomously. In your operation, this will all be autonomous, and the robot will just scan as it should be placing. So we just performed, about to perform our first scan. We just performed our first scan, and data should come in momentarily. So as you can see, the data came in at 8.54, 8.51, and 2.78. So these front hooks are actually much different than the other two sets of hooks. If you look at hook set number 2, and I'll go ahead and show you that one as well, just so you can see that that data comes in well. But the hook set number 1, hook row number 1, there's one of the hooks is the cutoff hook that we're swapping out with the 7 different hooks to do trials on. But also just the hook itself, the hook that is present, is also very much off in comparison to the other 2 rows of hooks. So I can even go and observe that through your right hand hook. And you can just see right here, we went from a 1 to now a 21. Actually a -1 to a 21. And you went from a -1 to an 11 here. And then we can go look at the left hand hook, and you can see the data come in off that. So we went from a -0.15 to a 15. So the data grew quite a bit. Now, if we find this is a passable, acceptable data and that the robot can actually still place to that, then we can modify our tolerances to be this amount, so that way we can actually place to these hooks. But as of right now, these hooks wouldn't pass an offset value, which would give us the ability to place. So I'm gonna go back to this offset to robots. You're gonna see we're getting a no good signal. We'll go look at like the left-hand status and see what we're getting. So we're getting no good on multiple of the inspections. Now I will say I think that these tolerances are low as of right now. These tolerances can be cranked back up. So this is a bent hook. I can tell you right now, I can tell from this data, this negative 6.72 is definitely a bent hook. That data is too much, whereas I think this 2.3 is still an acceptable data. We just have our tolerances set super low. This is probably a good time where I can just show you those tolerances. As you can see, after we changed that data to a tolerance of 3, now we're getting an okay hook. Now, like I said, the XYZ values are larger than what we would like to see in order to do a place. According to our engineering, we only have 3.5 millimeters of tolerance to be able to place the hooks and accurately place the hooks without dropping the part or crushing the part into the rack. So let's go look at our right-hand hook and see if we're getting the same from it. Okay, so as you can see here, our twist is okay, our hook offset is okay in the Z direction, and our bend is okay. So you can tell that the left hook is much more damaged than the right hook. And also a good thing to take note of is looking at the robot, your left hook is your left hand, your right hook is your right hand. So it's definitely a good thing to keep in mind so that way you don't get left hook and right hook mixed up for one another. So we're gonna do one last shift. We're gonna go ahead and scan the middle row of hooks, and then this will give us a different result. And I think the data will come in much better. We'll just stay on this screen until the robot scans. The robot's going to the top of the scan position right now. Robot scanned. Should see new data here soon. Okay, boom. Yeah, so I think our tolerances are just way too low right now. These tolerances just haven't been adjusted. Okay, let's go ahead and go over to the left-hand hook. See what kind of data we got on it. Okay, same thing. Just the bend, this is just the HMI value. You know, our primary focus has been on the actual engineering, the making sure that all the data works and all the data is coming in appropriately. The threshold is kind of a simple thing. As long as we can shift around and the data shifting around in the way that we expect it to, then all things are good. And as of right now, that has been the case. Let's go ahead and look at the right-hand hook offset values. So as you can see, they dropped down by quite a bit more in comparison to what they were from this other one. So this would have been a passable offset value. And let's go ahead and go over to left hand real quick just so you can see those values. Those dropped all the way down almost to a 1. And then let's see what values we would be passing to the robot, 2.87. So these are like your total values after the math has been applied. And this would be the main thing that you're looking at on, like, did it pass or fail? Which one did it pass or fail on? And then according to that, you can go look at the right-hand hook and the left-hand hook to see if one of them was grossly out of tolerance in comparison to one another. Now, I'm gonna perform one last test that'll just help demonstrate the robot's data. So what I'm gonna do is I'm gonna actually shift the robot's scan over by 15 millimeters in the positive X direction. So this data will come through and you should see this data go up to almost like 18. So you'll probably see like 17.9 as the new data that comes in from this hook. It will take a scan to update. Boom, there you go, 18.27. So that's what we'd expect, right? We added 15 more millimeters in the X direction. The X value changed, the Y value didn't, the Z value didn't really. And these are all perspective into how much data. Obviously, 15 millimeters is a much more substantial amount of data than the point data that you see here. These are point millimeters right here, so very tight tolerance. And the system is very, very repeatable.